Let us briefly examine the generic phase diagram for any pure substance A. First, we should briefly discuss what we mean by phase diagram. We learned in the fundamentals chapter that any pure substance in the ideal gas state is characterized by the equation of state PVM equals RT that relates the molar volume to the pressure and the temperature. Other states of matter are also characterized by equations of state. While these equations of state differ in form and complexity, they share one common feature with the ideal gas equation of state. And that is that they are expressed as a relationship between the pressure, the temperature, and the molar volume. The phase diagram of a pure substance therefore can be viewed as a three-dimensional representation with axes of pressure, temperature, and molar volume, showing regions where each phase is thermodynamically stable. By thermodynamically stable, we imply that at a given temperature and pressure, the molar volume of a substance is independent of time in that phase. For reasons of clarity, phase diagrams are typically shown as two-dimensional representations of pressure versus temperature for a fixed molar volume, or pressure versus molar volume for a fixed temperature, again showing where each phase is expected to be stable. At the closing of this lecture, we will provide a justification for why phase diagrams look the way they do. We will focus here on phase diagrams that are two-dimensional representations of pressure versus temperature and ask a relatively simple question. What does it mean when we say that, for instance, a liquid phase exists as a stable phase at temperature T1 and pressure P1? Let us assume that the substance A of interest exhibits only the three usual solid, liquid, and vapor phases. Stating that the liquid state is stable at T1 and P1 is the same as saying that the transformation A solid at T1 and P1 to A liquid at T1 and P1 and A vapor at T1 and P1 to A liquid at T1 and P1 are spontaneous processes. It is also the same thing as stating that the change in the molar Gibbs energy for the fusion and the condensation processes are negative, that is, delta fusion G sub m less than 0 and delta condensation G sub m less than 0. From the former inequality, we conclude that the molar Gibbs energy of the liquid state must be less than that of the solid state. From the latter inequality, we conclude that the molar Gibbs energy of the liquid state must be lower than the molar Gibbs energy of the vapor state. This allows us to conclude that the liquid phase is stable if its molar Gibbs energy is lower than both the molar Gibbs energies of the solid and vapor phases. We can represent the results obtained on the preceding slide by stating that the liquid state region is where the molar Gibbs energy of the substance is lowest for the liquid state. Obviously, the same reasoning would apply to the solid and vapor state regions. This line of reasoning also indicates that solid and liquid regions share a set of states where the molar Gibbs energy is the same in both phases. This is the set of states where the solid and liquid phases coexist. We call this curve the solid-liquid coexistence curve. Similarly, we define the solid-vapor and liquid-vapor coexistence curves. Now, to establish the location of the phase boundaries or coexistence curves, we will compare phase stability at different pressures for the same temperature or at different temperatures for the same pressure.